Great. Okay. Well, thanks for coming. Sorry I can't be there. As you know, I got COVID last week. Uh, I'm no very little symptoms. So I'll be coming later in the week. So I'm going to talk just some very basic stuff about Grassmannians. Some of it you can find in this book of Fulton, which is a nice textbook reference that Anna and I decided to try to follow. So let me start out. Let's let E be a vector, be an m-dimensional complex vector space. So those are my parameters. Actually, any field will do. Well, pretty much any field will do if you have the correct cohomology theory. And then I want to fix a number k between 1 and less than m and bigger than 1. And then our hero today is the Grassmannian of k planes in E, which is just the set of all k-dimensional linear subspaces of E. Now, because I'll be needing this, I'm going to set n to be the difference of m and k. People know what I'm doing. And if you choose a basis, E1 up to EM of E or for E, then you can identify E with C to the M, and I'll write GR KM for the Grassmannian of K planes in E space. It's useful to have coordinates sometimes. We'll almost always have a torus or even in fact a Borel chosen so that an ordered basis is natural. Okay, so the next thing I want to define is something called the Stiefel manifold. And this is the set of matrices so these are short and wide matrices such that the rank of M is K. So these are full rank K by M matrices. And now, given such a matrix, you can take its row space, and this gives you a K plane. And in this way, we have a map from the Stiefel manifold to the Grassmannian Km. I'll call it pi, and it's actually, let's see. So just to check out what the fiber is. If I take an element of the Grassmannian, then sorry, I haven't lectured on this small of a board since the pandemic, since well before the pandemic ended. Then the inverse image of H. Well, it's going. What I'm going to do is I'm going to consider such a matrix. It's the row vectors of this matrix. Well, I'll let. So elements of this I'll consider a point in inverse image. I'll think of it as a list of row vectors v1 up to vk. Such that these are a basis of H. Of course, because any collection of basis vectors I can put together to give me a matrix of this form and vice versa. And in this, of course, what you notice is this is isomorphic to GL KC, but not canonically. And this is a typical example of what's called a fiber bundle. And this, in fact, is the principal GLNK bundle. And in fact, the second exercise that I passed out is supposed to show is for you to verify. I mean, there's not too many steps to do it other than maybe show it's an actual bundle, that this is a principal GLMK bundle, or GLK bundle, I'm sorry, GLKZ bundle. Okay. The reason I want to introduce the Stiefel manifold, though, is not because I'm thinking about it as a principal bundle, is that if I take a subset, any subset Y in the Stiefel manifold, then it provides what we call Stiefel coordinates for its image in the Grassmannian. So for instance, the whole Stiefel manifold, we can think of it as being some set of coordinates for the Grassmannian. It's because it's a bundle, it's somewhat over-parameterized. But this is very useful, for instance, if you want to solve equations in the Grassmannian, or studying local coordinates, this provides a system. This is the general framework for providing systems of coordinates. Okay. And a useful such are follows. So I'm gonna use a combinatorial notation for M is the set of numbers 1 up to M. Anytime I have the square brackets, and then the set M choose K. This is all the K element subsets of the numbers 1 up to M, and I'll write a typical one. I'll assume it's always in order. So if I take an element of this, I'll write this as alpha 1 less than alpha K as a typical element of this set. And these are my standard indices for most of the day today, at least this hour. Okay, and then if I have an element of the Stiefel manifold, then M restricted alpha is the K by K submatrix of columns from M indexed by alpha. So you might have you simply take the collection of columns that you see, and you pull them out, put them together in a matrix. And now an important definition is the alpha Blücher coordinate, which is I'll write P alpha of M. This is simply the determinant of M restricted to alpha, and these are functions that are defined on the Stiefel manifold. And an important subset for us will be the subset of the Stiefel manifold, where M restricted alpha is simply the identity matrix of K by K matrix. So for instance, when alpha is the numbers 1 up to K, then U alpha is simply the set of all matrices that have an identity, that have a block matrix that looks like this, where the first K columns are the identity matrix, and then the remaining is any matrix of size K by N. Okay, and if you choose a different subset alpha, you simply shuffle this picture. So and this is a subset of the Stiefel manifold. Now, simply because this automatically is full rank due to the first due to this restriction, it tells me that this is isomorphic to C to the K times N. And people there are many words for this as the big cell or a big cell of the Grassmannian. And it's easy to see that the map pi from U alpha to the Grassmannian, it's 1-to-1, simply because you can look at it in this case when alpha is the numbers 1 up to K, and you can see the matrix is already in reduced echelon form. And in fact, if you have any matrix where the alpha Blücher coordinate is non-zero, then you can do row reduction on just that block of the matrix to get an equivalent matrix in U alpha that has the same row span. That's another way to see that it's 1-to-1. Now, and in fact, I just indicated that to you so here's a fact, and it that follows from what I just said, is that the Grassmannian of K planes in M space is the union of all these all these U alpha here, because this map is 1-to-1, I'm gonna identify its image in the Grassmannian with this set in the Stiefel manifold. That's also common. And now your first exercise is to show that these form a system of local coordinate charts, actually algebraic coordinate charts for the Grassmannian, and showing that the Grassmannian is a manifold, complex manifold of dimension k times n. And this is one of the ways to do that. So now the next thing to quickly, I'm quickly going through properties of the Grassmannian and some structures on it. The next one to refer to, I've already foreshadowed that with this definition, but there's okay. So I'm going to consider an element of the Grassmannian, then it's a subset of E, and there's a functorial map, namely the kth exterior power. I will not define this. You can if you need help, people can talk about this in the exercise session, where it's functorial. So it takes this inclusion to this inclusion. Okay. Now, because H is k-dimensional, this is a one-dimensional vector space. So this map takes me from a k-plane in M space to a one-plane, a line in this larger dimensional space. And so this gives a map. This gives the Plücker. Well, it's the Plücker map, but in fact it's an embedding from the Grassmannian of k-planes in M space to this projective space E, which is it's really it's M choose k minus 1. So this is the number of coordinates, and it's minus 1. And now let's see. So now if I have an element in the Stiefel manifold, one of my matrices that's representing a k-plane, I can think of this as I can take the map that simply takes me to the vector Plücker coordinates, and this this is a well-defined map from the Stiefel manifold to this large projective space. Let me just write a capital N for this number, because I don't want to keep writing it out. And now one thing to observe is that this map. So I have two maps. I have this functorial map, that I have on the Grass set. It's a set theoretic map, and then I also have this map from the Stiefel manifold, and it's not hard to see this factors through the map pi. In fact, this map is well, if I give this guy a name P for Plücker, this is actually P composed with pi, and that's something I asked you to check in the exercises. It's not so hard to see. You just have to write out, if I have a matrix, it corresponds to a list of vectors v1 up to vk, whose span is, well, I'll call the span H, and then this map here then is v1 wedge vk. So this composition, but if you write vi is some mij ej, and then you plug it in here and expand it, you'll get the Plücker Plücker vector Plücker coordinates coming out. This is just an exercise. I guess I'm giving you the outline of the exercise. Okay. Okay, so I was speaking rather fast. Any questions now that I can take a breath? Everybody knows, well, of course, I mean, a lot of people in the audience know a lot more than I do. I can see that. Yeah, sorry this isn't as interactive as it could be, but it's the best we can do given the circumstances. Anyways, so it turns out that okay, so there's a question about how do you put an algebraic structure on the Grassmannian, and I gave one indication by you could think about gluing these charts together. Some people like that. Another way is to argue directly that this map is well, this map is an embedding. This map, the image of this map is a smooth closed subvariety of Pluker space, and that's not hard to do by using these coordinate charts and the standard affine open charts of projective space, and that's also in that exercise I asked you to do. This is one of the cheaper ways of showing the Grassmannian as a manifold if you don't have a lot of group theory behind you. My lecture at the end of the day, I'm going to talk more about the groups that are going on, that are acting on here, and we'll see another way to view these flag manifolds. But let me dive into the internal structure of the Grassmannian, because this is where well, it's where Schubert first arises. So let me so I'm going to fix alpha, again, my favorite index, M choose K. And I'm going to define a subset of in my coordinate chart U alpha. And I'm going to draw a picture to see this a little more clearly. So this is a subset of U alpha whose coordinates are 0 in columns bigger than alpha. So, for example, I'll just, I mean, suppose here this is 3, and say M is 7, and I've chosen 2, maybe 2, 3, 5 is alpha. So, of course, because I'm in U alpha, I'll have an identity matrix in these columns. But then in column 4, column 1, 4, 6, and 7, I can put anything I want. But if I was in U alpha, I would have a 3 by 4 matrix of indeterminates. But here I've required that these entries are 0 to the right of the pivots. And so what I'm left with is a matrix of this form, and you can see in this case with 2, 3, 5, there's 4 free entries. This is a notation that I learned from Fulton. I just put a star in to refer to some variable. These are all different variables. So what do you do is you have U alpha, and then you set equal to 0 all the entries to the right of the pivots. These are called pivots from the standard pivoting algorithms for reducing matrices. And you can see that this is a matrix which is in reverse row echelon form. If you if I took any representative of a cape, if you take a matrix, any matrix, you can start scanning and you find the first column which is non-zero, which has a non-zero entry in it. Then you can divide to make that entry 1, put that 1 on the bottom, and then reduce the rows above it, and then continue until you continue with the remaining columns. And when you find the next non-zero entry in the remaining column, make that a 1 and use it to reduce everything above and below it to 0, and then keep going. And this is echelon form. So this is what you get when this is what happens when Gauss met matrices, sets like this. Okay. I want to emphasize that this is really fairly ancient. Some of the geometry behind what we're looking at. All right. And yes, so now, as I said, if you do this, if you do this Gaussian elimination, what you find, this implies that the Grassmannian, I guess sometimes I put the R and sometimes I don't. I should probably just skipped it. The Grassmannian is a disjoint union now over all alpha of these pieces. Simply put, if you take any matrix in the Stiefel manifold, you can reduce it to a unique one of this form, and it's pretty clear that any two such matrices are equal if they give you the same K-plane, if and only if the matrices are the same. That's what row reduced echelon form does for you. And so we get this decomposition. So earlier we had a decomposition which was as a union where there are lots of overlap, and there's no overlap. And this, okay. So now, this is called the Schubert decomposition. Not so much that Schubert came up with it, but because, well, it's related to these are called Schubert cells. And so exercise 4, you're supposed to show that this guy is isomorphic to C to some number, where this number is simply the sum alpha I minus I. So this is a measure of alpha. It's a sort of an L1 norm of alpha, but shifted in such a way. And this is called a Schubert cell. Now, this is, I mean, one of the main objects that people study geometrically here are Schubert varieties, which I'll define in a moment. And this is the big part of the Schubert variety. It's also, in some sense, the least interesting part if you like singularities or other stuff. Okay, so let me make some notation, because I need to be a little more flexible than just my matrices. So, and unfortunately, this is the problem with the small board. I erased something that would be very useful. Let me let EI be the span of my first I basis vectors. So this is a subspace of dimension I, and so I'm going to have E1 is contained in E2, contained in EM, which is E, and this is called a complete flag. Well, in fact, this is also called this one in particular is called the coordinate flag, because it comes by just looking at the spans of the coordinates, and it's a complete flag in that it's a complete filtration of the vector space, and it's called a flag because if you have a 0-dimensional space and a 1-dimensional space and a 2-dimensional space, well, let's see, let's get it right. Okay, well, you get a flag. That's really where it comes from. But this is the standard coordinate flag, and then from the, here's a fact which you can work out from the definition I gave of the matrices. It would be easier if I hadn't not erased this. I'm sorry. Is that a K-plane is in the Schubert cell if and only if, and this geometric definition is very important. It's the beginning of everything that comes later. If and only if the dimension of H intersect E alpha I is I, and the dimension of H intersect E alpha I plus 1 minus 1 is also equal to I. What this means is, okay, I will go back to my previous matrix, right? And I guess, and then zeros afterwards. With I guess so much for my coloring choice. So here E alpha 1 is E2, and this says that H intersect E alpha 1 is dimension 1, and since E alpha 2 is 3, this is empty. it's E alpha 3 is the span of the first three vectors, and it says the dimension of H intersect E alpha. I'm sorry, E alpha 2 is 3, and so H intersect E alpha 2 is dimension 2. E alpha 3 is 5, and 5 minus 1 is 4. It says the dimension of H with this space is also 2, which gives me the 0 here. And finally, it goes up to 3 when I get to E alpha 3. So there's this geometric definition, and people sometimes don't include this condition if you write it down. I think, like, I remember being confused when I was first learning of this from Griffiths and Harris, who did not define the Schubert cell all the way. Okay, so this part's a little clunky. But it's a little easier if you talk about the Schubert variety. I'll just write X alpha, which I'll also write X alpha of E. I'm sorry, I should call this coordinate flag E with a dot. It's okay because it's respect to this flag, and this is simply the closure of the Schubert cell. And this has a little more description. This is all H such that, or a little easier, such the dimension of H intersect E alpha J is greater than or equal to, I'm sorry, I'll use I, is greater than or equal to I. And you can think about why this gives you the closure of this set. And so what we see here is the Schubert varieties have a very appealing geometric description. They're the collection of K-planes that have a fixed, okay, so for a given flag, in this case the coordinate flag, they're a collection of K-planes which have at least a certain intersection with certain elements of the flag. This, you might think of this as the attitude. It's how much they meet the flag. So for instance, it has to meet it at least this much, but it can meet it more, and that's what the closure gives us. Now, of course, I've been alluding this. This makes sense. For any flag. Okay, that's the first thing. And the second thing is this will imply, these conditions will imply the same sort of conditions if you, let's see, how do I do this? Well, no. So if I take anything larger, well, okay, I'll just say it, that it's not hard to see that X alpha of E dot is contained in X beta of E dot if and only if alpha I is less than or equal to beta I for all I. So the containment of these geometric sets, and again, you just look at this condition, is equivalent to this component-wise comparison of these sequences. And so that this gives me a combinatorial structure on my subsets, and people call this the Bruchau order. And the study of these orders, which arise, and you'll see more of them today, is somewhat fundamental to the subject. They're particularly for the Grassmannians, it's a wonderful order. Okay. And one of your exercises asks you to explore Schubert varieties of the first interesting Grassmannian, the Grassmannian of two planes in four space, which I will not be around to enjoy people doing that. Okay. So one thing which is okay. Now, this is a subset of the Grassmannian. In fact, it's a closed algebraic subvariety of dimension alpha, the absolute value of alpha, and I can take it. This gives me a homology class. It's in the homology of the Grassmannian, and then I can take the this is the this is the cohomology class, which is, oh gosh, Poincaré dual to the fundamental cycle in homology. So this lives in where does it live? It lives in H2 Kn minus alpha of the Grassmannian. So this is a cohomology class. I'm just jumping right to cohomology because that's where the interesting algebra lies. And these are okay. So every Schubert, well, every index and a flag gives me one of these. Now, because the general linear group is connected and any two flags can be moved from one to the other by element of the general linear group, this class does not depend upon the choice of the flag. And so it only depends upon alpha. And that's the case for ordinary cohomology. Now, because we have this paving of the Grassmannian by these affine subsets, by the open parts of the Schubert cells, any number of results, in my favorite being cellular homology, but you can also use Burrell-Moore cohomology or many other ways to think about this. Because of this, this implies what's called Schubert's basis theorem. And what it says is that the cohomology of the Grassmannian is equal as a free module over the integers to simply these classes form a basis for the cohomology of the Grassmannian, also the homology. I mean, they form a basis for the homology. They're an even degree, so by universal coefficients, they form a basis for cohomology. Okay. There are many ways to see this, and so these are geometrically interesting classes that are fairly easy to describe. There's not too many of them, and they tell you everything about at least the cohomology ring. Now, for many reasons, it's better when it's better in general to change the notation from sequences to partitions. And one of the tensions of the subject, or at least one of the annoyances, is the need for different notations for how we index things. But partitions are often, I mean, and you see other ones during this week. Partitions are a very alluring way to talk about the cohomology of the Grassmannian. So let me introduce partitions, and then get a little more into studying these classes called Schubert classes. I'll just call these are Schubert classes. Okay, so I'm going to define a partition lambda, which depends upon alpha. And this is a transformation from sequences to partitions and back again. And what is this? This is the sequence n plus 1 minus alpha 1, which is up to n plus k minus alpha k. Now, because I'm subtracting alpha 1 up to alpha k, this should be decreasing. Because I'm adding, each time I'm incrementing, this is n plus 1 minus alpha 1, n plus 2 minus alpha 2. Because of that, this will go down, not strictly, but weakly. So this is a somewhat more efficient encoding of the sequence. So this will be some number. This is at most n, and this is, and you can check, this is at least, yeah, this is less than n, and this is greater than 0. So people like to think about partitions. Well, I'll just an example. I had 2, 3, 5, and that's going to go to, so here n was 4. 4 plus 1 minus, so yes, 4 plus 1 minus, Okay, now I'm a little bit troubled by this suddenly. Okay, yeah, well, okay, 4 plus 1 minus 2 is 3. 4 plus 2 minus 3 is also 3. And 4 plus 3, 7 minus 5 is 2. Okay, so this sequence goes to 3, 3, 2, and people like to write this, well, people like me like to write this as a sequence of boxes where I have lambda I boxes in the ith row. And this sits inside of a rectangle of size k by n. Okay, so that's and this is a fairly now also I need to write the absolute value of lambda. It's the sum of the parts of lambda, and that's easy. That's easy to see. That's k times n minus the absolute value of alpha. So the reason this was defined, this ended up being the dimension of the Schubert variety, and so this is the codimension. This is the codimension of the Schubert variety. And I'm going to write sigma sub lambda for this cohomology class. Remember, it doesn't depend upon the flag. That's one reason I'm skipping notating the flag. Now that given this, then we see that the cohomology has a basis given by these Schubert classes, given by partitions now inside of this box, and you can check there's the same number of them. There's many cute ways to think about going back and forth between them that were discovered a long time ago. And what happens is because I have this is a free module, an integer basis. It's also a ring. So there exists a unique number c lambda mu nu in the integers for nu mu lambda partitions. So inside of the box, where defined by if you sigma mu times sigma nu. Well, this is some element in cohomology, so you can write it in terms of the basis, and these are well defined. Notice that this is not that this guy is not equal to 0 if and only if well, because the cohomology is graded, if and only if you have this. And so you might as well restrict the summation to that. So there's these well-defined integers, and that's a consequence of Schubert's basis theorem, which he derived in the 1880s using other means, of course. In fact, he didn't have cohomology at the time, and so this is more, well, there's a wonderful story behind making Schubert calculus rigorous. So we have these well-defined numbers. Yes? What? Oh, I'm sorry. Thank you. Okay, Alan, yeah, Alan knows that better than the rest of us. Yeah, thank you. Sorry, I just had COVID, you know. No, but I didn't have any brain fog. No, I just wasn't thinking. You know, it's the usual thing when you touch the board, your brains go away. I mean, I'm also looking ahead. Yeah, thanks. Yeah, this is a very interesting story. I mean, it's really amazing mathematics here and real wonderful results behind it. Actually, I don't have time for that. Okay. Now I want to point out that there's this largest partition of size k by n. This is the class of a point in the Grassmannian, and there's a map called the degree from the cohomology of the Grassmannian to the integers that just simply if you have a class in the cohomology, it takes it to the coefficient of point in this class. So this is the degree map. It's also called integration if you're doing de Rham cohomology, but I'm just going to call it the degree. It's the push forward to a point in homology. I mean, I guess, well, it comes from that, so it's a little, I'll leave it at that. Now, there's the next major theorem in Schubert calculus is Schubert's duality theorem. And so if lambda plus mu is k times n, so these are these index classes whose product will be in the top degree cohomology. Then if you look at the degree of sigma lambda times sigma mu, well, it's 1 if lambda I plus mu k plus 1 minus I equals n for all I, and it's 0 otherwise. So what it says is under this there's a intersection pairing, or you multiply two elements together and take the degree. I mean, you don't need this, in fact, for this to be true, but I'm mostly interested in this case because that's the only case when this could possibly be non-zero. And it says that the product of two classes followed by the degree, it's that the Schubert basis is self-dual under this. And now I'm going to give a quick sketch of this, but it has well, now my proof of this uses I'm going to use that a transverse intersection corresponds to a product, and these and the arrows here do go both ways in this case. Namely that if you have A and B are subsets of the Grassmannian that intersect transversally, that meet transversally. I mean, you can have a weaker condition this, but I'll just say this. Then if I would take the product of their classes, that would be the same thing as the intersection of the class of the intersection. So that's why people call product the intersection pairing, because you can I mean, in fact, one of the reasons for cohomology, ordinary cohomology, is the idea to replace something very hard like determining how subvarieties meet by something easy like algebra, where you can just apply the rules of algebra. This is, in fact, was the original idea in the later part of the 19th century that started with Sottile and went on through Schubert and others. But when things meet transversely, the product can be computed by an intersection. And there's also, let's see, there's also, oh gosh, no, okay, now, let's see, what do I want to say this? Okay. I'm just looking at my time and I realize I will not get to cover everything. So just pausing for a second. Yeah, okay, so the way to prove that is that you start out with flags, two flags in linear general position. That means that the dimension of EI plus FJ, well, the dimension of EI plus FJ is the minimum of M or I plus J. I think that's correct. I wrote down something else, but that should be correct on the fly. It says that there are far apart as possible. And then, okay, then there's the okay, then there's a lemma you prove that says that X alpha that under this assumption that they're in linear general position, this is not equal to the empty set if and only if alpha I plus beta k plus 1 minus I is bigger than or equal to m plus 1. And this comes about from the condition that so H intersect E alpha I has dimension at least I, and H intersect F beta k plus 1 minus I has dimension at least k plus 1 minus I, and so these two subspaces of H have to actually meet. So the section has to be non-empty. And then in particular, it has to have a dimension of at least 1. I'm sorry, not empty, non-zero. And the condition that these two things meet in dimension at least 1 is this. Okay. And let's see. So one, and you then in the, then you show that when this happens, this condition, yeah. So you show that this, when this happens and you have this condition, then this must occur. And so the only case where this product could be possibly non-zero is in this case. So this implies that we must have lambda I plus mu k plus 1 minus I equals n, and then you argue in U alpha that and then the argument goes, you look in these local coordinates and you discover that in these local coordinates, I should say that I needed to choose F properly. I'm sorry, I'm trying to skip this proof because I want to get on to the Pierre formula, which I think is a little more important. But you argue in U alpha that remember in U alpha that I defined the Schubert variety where all the variables to the right were 0, and with the opposite flag, all the variables to the left of the pivots are 0, and then you see they meet transversely in a single point. So sorry, but and that then proves this theorem. This theorem has an important corollary. Because of this duality, what we find is that C lambda mu nu is the number of points in. So oh gosh. Okay. I need to make one definition, is that when this happens, this condition here, I'll draw a little picture for us. If this was lambda, this means that this is mu. So lambda and mu fit together in my k by m rectangle where mu is rotated and fit together. And when this happens, I'm going to call mu is lambda dual, and likewise, I'm sorry, lambda dual. Likewise, also the notion of okay. So I have this. So now what happens then is C lambda mu nu, it ends up being the number of points in a triple intersection of the form x lambda of E. So here I'm writing, well, I'm using the same symbol x, but here this is a partition. So I'm using the partition instead of the sequence. Intersect x, not x lambda, x mu intersect x nu of F intersect x lambda dual of G. Now, okay, that's when, okay, so it tells us that this number will be this triple intersection when this is transverse, which can be achieved by choosing the flags to be in general position, and that's a real theorem. Not the hardest theorem, and again, because these end up being complex manifolds, all the intersections are oriented, so every intersection point counts with a +1 in the homology. Okay, So in particular, this says that these are positive numbers or non-negative numbers, which is what makes them of interest to combinatorialists. So let me try to express. Okay, the last one I talk about is something called the Peary formula, and this. So Schubert came up with a version of this in the, I think, 1892 for Grassmannians of two planes in n space, and almost immediately afterwards, Peary, Italian mathematician, came up with the general form, and it actually ends up giving the ring structure to cohomology. And what's interesting is this was not under even though combinatorists were studying the same sort of objects, they didn't know of this formula until 1947 when Lesueur, I think that's his name, when he showed that the cohomology of the Grassmannian is roughly the same as the multiplication of symmetric functions. So I find that a little bit of interesting history as a geometer. So so let me let A be this partition. So it's just a single box. It's a single row where there are A boxes in a single row. And I'm gonna start using partition notation for this. And then it says that if lambda and mu are partitions with, so mu plus A equaling lambda. The corresponding Littlewood-Richardson number, or I'm sorry, these have a name. I'm sorry, these structure constants are called Littlewood-Richardson numbers. So this is it's either 1 or 0, just as before, but it's 1 if lambda 1 is at least mu 1, which is at least lambda 2, and so on. Mu k, no, lambda k, mu k, and it's 0 otherwise. So this, let me indicate with the picture an example of this. Okay, so if this is mu, and if say A equals 3, then I have to have a partition lambda, which is where each of the parts are at least the same size as mu, but they can't be, well, so here's an example of a partition lambda which is bigger than mu, but it does not fit this condition because lambda 1 equals mu 1, lambda 2 is bigger than mu 2, but lambda 3 is also bigger than mu 2, and it should be less than mu 2, or less than or equal to mu 2. So here, this is an example of something which is permissible under these conditions. Another way of saying this is if you look at the difference between lambda and mu, there are A boxes and no 2 in any column. People call this a row or a skew row. But this is the Peary formula, and it has this interesting interlacing property here. Okay. So this I think is also roughly Schubert's proof, or I think also Peary's proof. There's a nice geometric proof of this, which is that. So I'm going to suppose that. Oops, I need a new piece of chalk. I'm going to suppose that E, F, and G are flags in general position. Now, E and F this includes being in linear general position, and we'll actually see, and we may actually see what this means if I get to the end of this. Then this Schubert variety, the one corresponding to condition A, is the set of all H such that dimension H intersect G, and what is it? N plus 1 minus A is at least 1. So this is called a special Schubert class, and it's given by a very simple condition that it meets a particular element of the flag. So remember, H is dimension K, and so if it were in general position with N, with G, it would not intersect this, but it would intersect this space in dimension 1, just by general position arguments. And it's saying it intersects a much smaller space in dimension 1. That's called a special Schubert condition. Then, okay. So then, let me call alpha is alpha of mu. Alpha I is n plus I minus mu I. So this is the correspondence between sequences and partitions for mu. I want beta to be alpha of this dual of lambda. Again, because I'm going to be arguing a triple intersection proof of this, so I'll need to use the dual of lambda, like I briefly wrote down last time. And this is a little more. This is beta I is n plus I minus lambda dual I, which is, well, when the dust clears, it's I plus lambda k plus 1 minus I. So there's a little bit of, yeah. Okay, and that's going to be helpful. Okay, so then we're going to try to understand what does it mean for something to lie in a triple intersection of this form. So these are, so this corresponds to mu, this corresponds to dual of lambda, intersect xa of g. I'm going to suppose there's something in the intersection, and well, and then and this is going to tell us something special about the partitions lambda and mu. And then when that holds, we're going to discover there's only a single point in the intersection, and it's equivalent to this condition. It's a fairly classical triple intersection proof. So by exercise 6, what happens is, okay, so exercise 6 asks you to show that when this holds, this implies that H is a subset of something called V, which is the sum over I of E alpha I intersect F beta K plus 1 minus I. And I should point out, in exercise 6, there's a typo. So there's a typo. There's some place where I have beta minus 1, and it should be replaced by beta. No, it's k minus 1. It should be replaced by k minus I. It's beta sub k. Beta sub k minus 1 should be replaced by beta sub k minus I. Thanks to Alex for pointing that out to me. Okay, so this. So once you, okay, I'll stop in a minute. Once you have this, you discover that the dimension of V is less than or equal to k plus a, and this condition implies that V intersect G n plus 1 minus a has dimension at least 1. And these are the only way that if G is in general position, the only way that this can happen is if this dimension is equal. And then in that case, this becomes a direct sum. Then this implies this interlacing property. And finally, it tells you that there's exactly only one that because this is a direct sum and H has to contain this intersection, H is, well, it has a special form here, and I'm going to stop talking about it because I don't like to go over time. I could provide details, but I just don't like to go over time on people's time. And sorry, I slightly over prepared. Okay, silent clapping because I can't hear anything. Sorry about that. Yes? I can't hear you. Yeah, maybe the mic is not connected up to the... Yeah, but I don't know if I hear you through the microphone. Tap the microphone. Tap the microphone.
Just speak loudly.
All right, can you just go over the definition of degree?
Oh, okay, so degree, yes. So, okay, so this is a map we have in cohomology. You can have a I have some cohomology class of some manifold. Okay, and then I take this, and there's the cap product with the fundamental cycle of the manifold, and this will be okay, and so this will be an element of the homology of the manifold, and the and then okay, so I'm giving you the yes. No, I'm giving you the formal definition. You take an element of cohomology. You can take the cap product with the fundamental cycle of the manifold, and this would be in the homology. And then there's a map from the manifold to a point. And so then you follow this through by the map to the homology of a point, which is just the integers. And okay, so that's this composition is the degree map. That may not tell you very much. So in what this amounts to, okay, so what okay, so that maybe that's not very helpful, but what happens is okay, that's the formal definition, but what this does is the top dimensional homology of the manifold is Z times the class which is Poincare dual to a point. This gives me the Poincare duality, and what degree does is degree of a class is simply the coefficient of this generator in gamma. Now, okay, so for our case, for the Grassmannian, here the class of a point was simply the Schubert cycle indexed by this k by n rectangle. So it's simply reading the coefficient of this object off in a product. In the case, if you're using de Rham theory for cohomology, then it simply is integrating. I mean, this cap product and followed by the push forward to the point can be obtained by just integrating that cycle, that top class over the whole manifold. So some people will also write integral for it, and it's the same map. When we're doing intersection theory, where we're intersecting cycles, when they meet transversely, it'll be a finite set of points, and the degree is simply that number of points, or the number of points weighted by the multiplicity of the intersection. Okay, does that help? I mean, the origin of this term is if I have a curve in the plane of degree 3, and I take a general line in the plane, it will meet that curve in 3 points. And that meeting is the intersection product in the cohomology of the plane, or the Chow ring of the plane. Okay, does that, yeah. So that was this whole lecture was a little bit quick. I was rather, I mean, I wanted to cover some of the basics of Schubert calculus of the Grassmannian in an hour, and I thought I could do it. Well, maybe not. Maybe not everything with reasonable proofs. And of course, I was force feeding you a lot of mathematics. Yeah, sorry I can't be there to talk to people, but you can like rag on me when I get back, when I show up there. Yeah, those exercises are I'm hoping that they're somewhat straightforward. I didn't want to get anything very complicated, but they sort of reinforce things that I said in the lecture mostly. So thanks a lot. I'm gonna come off, and I'm gonna try to listen to Anna's talks. Okay.
a reddish light? Okay.
That should be good, but try speaking.
Testing, 1, 2, 3. Can you hear me? Okay. All right. Sorry, I had a last minute tech thing pop up. Okay, so hopefully Frank can hear me now. Yeah, so this next lecture is going to be much more combinatorial than the first one, but we're going to build on some of the things that Frank told us about Grassmannians, but think about this cohomology ring in a different way using Schur polynomials. All right, so last time Frank told us about the Grassmannian of k-dimensional subspaces of C to the m. And in particular, we saw that we can think about this as being this these formal linear combinations of the Schubert classes. And what we really want to understand is how to take two Schubert classes multiply them together, and expand them out in this Schubert basis. And we got a proof of the PRE formula in particular, where we're multiplying by a special partition that's just a single row. Okay, oh, it's being slow. There we go. Okay, so in this lecture, we'll take a more combinatorial and algebraic perspective. So we'll start by discussing Schur polynomials, and then we'll move on to some discussion of tableau combinatorics. And in particular, we'll look at this Littlewood-Richardson rule that tells us completely how to compute these Littlewood-Richardson